In this video, we will cover 7 different activation functions that are commonly used in neural networks. Neural network activation functions are used to control how artificial neurons respond to inputs. Now, with the exception of the linear activation, all other activation functions introduce a nonlinearity into the neural network. Now, this enables the model to learn highly complex relationships that may be present in the data. Now, first, I will very quickly go over what neural networks are and what role does activation functions play within neural networks before we go through our list of 7 activation functions that I want to cover in this video. Now, neural networks comprise a broad family of machine learning models that emulate how biological brains work. So in biology, a brain is composed of a series of cells. These cells are called neurons, and these neurons are interconnected with each other. So these individual neurons receive signals, and these signals can come from other neurons within the brain, and these inputs are called dendrites, and these input signals are then processed within the neuron itself, and then an output can be released from the cell along what's called an axon. And this axon can then run off and connect to other neurons within the brain. So this is at a very high level how brains are structured and how signals and information can cascade through the brain. So in the case of a neural network, we seek to emulate this structure. So what we have is a set of inputs, and these are indicated here in this figure as x1, x2, and x3. So this particular neuron has just 3 inputs, and these are then sent into the individual neuron. The neuron computes a linear relationship between the inputs, and that linear relationship is given by Z. Z is equal to B, which is a bias term, and then that's plus the dot product between the weights and then the inputs that have been received in. So this is a weighted sum of the inputs that have been received by the artificial neuron. And then we take that linear combination and we apply a function to it, and that's how we get our output y. And so the function here in the figure is shown as f, and f is our activation function. So this is what we're interested in diving into and seeing what kinds of different values for f can we use in a neural network. So the first activation function we'll cover here is called the sigmoid activation function. It's given by this formula, and so it has an exponential relationship between the input z and the output y. Now this function has a few interesting properties. It is smooth and continuous, which means that we can compute its derivatives, and its output is bounded between 0 and 1. So because its derivatives are easy to compute, this was a very popular activation function in prior years for building neural networks. That's because as part of our training procedure, we typically use backpropagation, and backpropagation requires us to compute the derivatives of the activation functions. One of the problems, though, that has come up with more recent development is that other types of activation functions also have these properties of being able to compute their derivatives, but they actually yield better performance. So with most modern neural networks, the sigmoid activation function is typically not used. An exception to this is the case where we're building a neural network to model a binary classification problem. In this case, we can still use a sigmoid activation function in the output layer to make a distinction between the 2 classes that we're trying to model. The next activation function we'll cover is the tanh, or the hyperbolic tan function. Now, it also has an exponential relationship between the input z and the output y. Like the sigmoid function, it is smooth and continuous, which means its derivatives are well defined throughout its whole range. However, its output is bound between -1 and 1. And that means that the output is centered around 0, has a mean of 0. So in practice, these activation functions almost always perform better than the sigmoid function. And so typically we use the hyperbolic tan, or we would choose to use the hyperbolic tan over the sigmoid wherever possible. The third activation function we'll cover is the linear activation function. Now this is the one activation function we will cover here that does not introduce a nonlinearity into the output of the neuron. So in effect, the activation function we have here is just the identity function. That is, that it just returns whatever input it receives. So you might ask, why would we bother with such an activation function? Well, in the case that we're building a neural network to model a regression problem, we would want to use a linear activation function in our output layer. And this enables our neural network to return an output value that has a full range of possible values. It's not bounded like what we saw with the hyperbolic tan or the sigmoid functions. So that's the practical use for a linear activation function. The next activation function we'll talk about is the rectified linear unit, or ReLU activation function. Now, most modern neural networks use neurons that have a ReLU activation function or some type of variant of the ReLU activation function. Now, if we look at how this function operates, it's a piecewise function, which means that it is 0 for inputs that are negative, that are less than 0 itself, and for any inputs that are 0 or positive, it follows a linear relationship. So it just returns the input. So this, because it's a piecewise function, it is also nonlinear, but the very important feature of these functions is that its gradient remains quite substantial at very large values for z. So the problem with the sigmoid or the hyperbolic tan activation functions is that they're both asymptotic, which means that as we move away from 0, from a 0 input, the function profile tends to plateau out. And that means for larger and larger values of z, we have smaller and smaller gradients. And this tends to really slow down training. And so to combat that, the ReLU activation function was developed. One problem with the classical ReLU activation function that we see here is that for negative input values, it's just flatlined, it's just 0. So a lot of variants play with this. We have the leaky ReLU activation function where this isn't quite just always 0, it actually dips down. It can be somewhat of a negative value. There are other variants where for negative values of z, the output follows a bit of an arc, also in the negative range of y. So there's a lot of different variants for the ReLU activation function. But the key thing to keep in mind is that for most modern neural networks, it's the ReLU activation function that would be applied within the layers of your network. Next, we have the binary threshold activation function. Like the ReLU activation, this is a piecewise function. In fact, it's a step function, or it's a heaviside step function, which means that for all negative values of z, we just return 0. Otherwise, we return 1. So it's just a very simple stepwise function. Now, in this case, we can look at this and immediately see that the derivatives for this function are either going to be 0 or undefined. And so for any neural network that relies on backpropagation, we can't use this type of function. It just won't work. So where do we apply this? Well, in perceptrons. So a much earlier form of neural network actually makes use of this type of activation function for introducing nonlinearities in its decision making. Now we'll talk about the Softmax activation function. And this is strictly used in the case where we're building a neural network to model classification problems. Now the form of this activation function is as follows, and it has this exponential relationship between the inputs z and the output y. And we have subscripts here that indicate the index for individual neurons in a given layer. So for an output layer in our neural network, for a specific neuron I, our output is defined given this formula, where J is the number of possible output classes that the neural network is meant to model. So J iterates over all possible classes, and in our output layer, we would have one neuron for each possible output class that the model considers. Now, the output, strictly speaking, does not include a class label. Instead, it's a probability for that class label. If we sum over all the outputs over all the neurons in our output layer, they will all sum to 1. So that shows us that the properties of the softmax function follow or are consistent with being a probability. The last type of activation function we'll cover here is called a stochastic binary activation function. And in this case, we use the sigmoid function, but it's not as the activation function per se. Instead, we use the sigmoid function to compute the probability of a given state to be true. So in this formula that we have here, we see our sigmoid function, and it's giving us the probability for state S to be equal to 1. And so if S can take on states either 0 or 1, then the probability of S equals 0 is just 1 minus P in this case. Then the probability that we compute here is input into a random number generator that will actually yield the output from the neuron. Now, these types of activation functions are used in energy-based networks. These include restricted Boltzmann machines or deep belief networks. So if we look at the output from this type of activation function, we'll see a profile as follows. We can see its random nature. However, for increasingly negative values of z, we see that the output tends to be 0. And this makes sense when we consider the probability of having 0 increases as we get increasingly negative along the x-axis. If we remember the profile that we saw earlier for a state equals 1. Conversely, for larger values of z, the probability tends to get higher that we return a state of 1 for ever increasing values of z. And this is again consistent with the probability profile that we saw earlier. So this concludes the video. If you're interested to look at the code that I used to generate these plots and go through these examples, please look at my blog article that this video is based off of. If you learned something from this video, if you enjoy this content, please like, share, and subscribe to the channel. Your support is greatly appreciated. Have a great day, and see you in the next video.